and welcome again to another interesting virtual Astronomy Day program with the North Carolina Museum of Natural Sciences. My name is Nancy, and I'm going to be the host for this program. It's going to talk about the scales of the universe. And with me is a very special guest, Ron Monty. And Ron is an outreach speaker for the Raleigh Astronomy Club, as well as a lifelong volunteer educator and exhibitor at the museum. And so he has been doing fantastic things for the museum. And he's also a science instructor for the Aldi Lifelong Learning Program at NC State. So he's very busy, and we're very excited to have him with us today. And as you know, we like to always start with an icebreaker question. And Ron thought it would be a good idea to ask you all, how many stars do you think are in the observable universe? And you can type that in the chat. Please don't use numbers. See if you can use words, because otherwise you might spam the chat. And while we are waiting for those answers to come in, and while we are waiting for everybody to get settled in Zoom and YouTube, I'm just going to go over a quick Zoom tutorial with you all. So as you know, this program will be recorded. So the participants, speakers will be turned off, and the videos will also be turned off. But closed captioning is available. So you just have to click on that little CC button at the bottom, and then there will be a screen that will pop up. So then you just click on that show subtitle. And when you do that, you will be able to select subtitle settings and choose the settings the way you want. Now, as you can see, we have our guests and our speaker boxes kind of like overlapping our slideshow. And so what we recommend that you would do is, you can see that we are now in gallery view. You can change that into speaker view. And then you will only have the speaker box right here. And then if you click on view options and you scroll all the way down to side-by-side mode, you will be able to have your speaker box next to your slideshow. And then you've got that slide bar that you can move to either to the left or the right to make your slides bigger or smaller. And then last but not least, we do want to hear from you. So please use that chat box, and any questions you have or any comments you have, put that in the chat box. But just remember to be good digital citizens. So don't spam the chat box, and also be respectful to our speaker and our moderator, Cindy. So, and with that, I'm going to stop sharing my screen, and we're going to see if we have some answers coming in. So Ron, I see tons of stars, 10 billion trillion, 5 billion, 9 billion, infinity. What is the answer? Do you have an answer?
Well, astronomers aren't really certain about the number of stars in the universe. They're all estimates. But when I started doing this talk about 5 or 6 years ago or more, I used the number of 40 sextillion, and that was at the higher end of the range of the number of stars. Now it's at the lower end of the range of the number of stars. So now it's not uncommon to see counts of or estimates of the stars to be like 200 sextillion or even a trillion. So maybe the James Webb will be able to shed some light on that.
Right. Maybe they have to come up with another word.
Yeah. So now I guess I can start sharing my screen.
That would be wonderful. Yes, if you could start the presentation, that would be great. Thank you.
Okay.
And we can see it.
Everybody see that?
Mm-hmm.
Sorry, I need to for a second. Okay, there it is. Okay, Um, I'll go ahead and start.
Go ahead. Yes, thank you.
Okay. So the title of this lecture is The Scales of the Universe. And it's about how can we possibly grasp the huge numbers that we see in science. Everything from the number of stars on the astronomy side to the numbers of atoms and things on the physics side and everything in between. So I'm going to start out with a quote from Gail Jones, who's a professor of education at NC State University, on the reason why understanding scale is so important. And she and her colleagues at NC State wrote this book called Extreme Science, From Nano to Galactic. And here's a couple of quotes. The first is, an understanding of scale and scaling is of central importance to a scientific understanding of the world. And then, though scale has always been central in science, an argument can be made that it has never been more important than it is right now. And why? Because when you understand the relationship of size of one object to another, you can better understand how they interrelate and interact. So now science is pushing the boundaries of scale. And here we have three examples of those. The first is upper right. You see the Large Hadron Collider, which is in France and Switzerland. It's a huge detector. It's in the shape of a ring, which is 17 miles in diameter. And it's probing the depths of subatomic particles and how they interrelate with one another. And just a couple of years ago, it discovered the Higgs boson, which imparts mass to subatomic particles. The next one on the lower left, we've heard a lot about recently, and there's been several talks at astronomy days about it, is the James Webb Telescope. And it just reached its station in space at the L2 Lagrange point, which is where the gravity is equal between the Earth and the Sun. And it's going to appear back in time to about 13.5 billion years. That's just a few 100,000 years after the Big Bang. So we're excited to see that come online after all the engineering marvels that have taken place so far unfolding it. And then also on the lower right is something called a LIGO detector, the Laser Interferometer Gravitational Wave Observatory. And this is in Washington State, and also there's another one in Louisiana. And there are several more around the Earth right now. And I'll be talking more about this, but this has arms that are 2.5 miles long to detect gravitational waves, which are incredibly tiny. And we're going to find out just how tiny shortly. So now here's an example of some of the numbers we're going to be talking about. And on the smaller side from nano, this is a quantum corral of iron atoms. And that's 1 nanometer, or 1 times 10 to the minus 9th meters in diameter. So 10 to the minus 9th meters is a decimal point followed by 9 decimal points. That's 8 zeros and then a 1 to show you how small it is. And then to the galactic and beyond over here on the right, this is the Whirlpool Galaxy, and that has a diameter of 180,000 light years, or 1.8 times 10 to the 21st meters. That's a 1.8 with 21 positions after that decimal point that you see there. It's going to be a 1 time 1 and then an 8 and then 20 zeros. So the difference in size between these two is 1.8 times 10 to the 30th. So what you do is you measure the difference between this minus 9 on one side and the 21 on the other, and the distance would be 10 to the minus, or 10 to the 30th power, 1.8 times 10 to the 30th. and that would be this number that you see here. Well, that's really amazing. But in this presentation, we're going to go even smaller and bigger than these. And how do you comprehend such an enormous range of numbers? You know, well, let's look at 5 cognitive tools that science educators use to deal with size, distance, time, and quantity. And here, we're going to go through each one of these. There's the zoom in, zoom out, scale models, timelines, analogies and proportions, and thought experiments. Each one of these can be termed a cognitive tool. And we're going to see examples of every one of those. So the first one is the zoom in, zoom out. And some of you may be familiar with the program Through the Wormhole with Morgan Freeman. It was several years ago. And in one of the episodes, he started out with a view of Venice. This is the center of Venice here that you see in the picture. And what he showed was a group of people in the square there, St. Mark's Square, and they put a hula hoop down in the middle of the group of people. And that hula hoop is 1 meter wide. And then what happens is he zooms out so that the next view you see is 10 times wider than that hula hoop. And that is this circle of people standing here. And that's 10 meters wide. So he zoomed out from 1 meter to 10 meters, and he keeps zooming out. So this is 10 times more, which is 100 meters across. You can see the center of Venice here, and he keeps zooming out and out and out until he sees the northern Italy here, and this is the Adriatic Sea here. You can see part of it. And he keeps zooming out until he comes out to the Earth, and even more. It'll keep going in the video until he reaches the solar system, the Milky Way galaxy, and all the way to the edge of the universe. And then in the program, he does the exact opposite. He starts at somebody, something small, and then zooms in. So you can see cells in a plant and molecules and then atoms and even smaller. So that's an example of zoom in and zoom out. One of the classic examples of the zoom in, zoom out is a book by Philip and Phyllis Morrison, who wrote The Powers of 10 a couple of decades ago. And it's a little bit dated right now, but it still is a classic. And it does the same thing as Through the Wormhole, but instead of in Venice, it starts out at downtown Chicago. And then a more recent book that's very good, that uses zoom in, zoom out, is called The Zoomable Universe by Caleb Scharf, which I highly recommend. Okay, so here is something called Scales of the Universe, which is a zoom in, zoom out, and it's one of my favorites. And here's a screenshot from it. It's a computer app, and it shows you the size of different objects and how large they are. So here you see the Earth. If you look down in the lower right corner, you'll see how large it is. So what this is, it's saying that it's expressed in meters, the Earth is 10 times, or it's 10 to the 6.9 meters in diameter. So that's the width of the Earth. And at that same scale, you'll see all these other objects. So you can see here's Mars. Mars is much smaller than the Earth. You can see the moons of, here's Saturn's moon and Mercury, and here's Asia and Venus. And so this program was developed by a pair of teenage twins, which is incredible. They could come up with something like this. Their name is Gary and Michael Wang, and they came out with this about, I guess, 7 or 8 years ago, and they're probably postdoc students now. They probably have their doctorates already, but it's an amazing program, and I'll show you how it works here. This is the website here. It's called htwins.net, and I believe that Nancy will be forwarding you the websites that I describe here.
Yes, definitely. Cindy is going to put that in the chat for everybody. So you
Okay.
can click on it and it will bring you to that website. Yeah,
Okay.
thank you
So
very
now
much.
here, when you first go into the program, you'll see something like this. And here, this is a ring that's 1 meter wide. So it's similar to that hula hoop that we saw in Venice. And at that same scale, which you'll see over here is 10 to the 0 power, which means it's 1 meter wide. Um, you see a human being and some other objects like a basketball and the largest flower in the world. And then you see down here this horizontal bar with a cursor in it. You hold that cursor down, you hold your cursor down and move it to the right, and you'll start zooming out. And now you move, here it shows where the cursor's been moved to the right and it's zooming out. So now you see the human is smaller. See, here's the human here, and you start seeing things that are larger. So you see a large cactus, an oak tree, and an elephant here, and a giraffe. And you can see it'll zoom out where you can see this brontosaurus up here and a whale. And you keep doing it, you zoom out more. Here's that view of the Earth and Mars and Asia, and Venus. And you can go much farther out. You can go way, way out to the edge of the universe. Here's another screenshot that shows a nebula within the Milky Way galaxy. Here's how far light travels in a day compared to the nebula. And then you can also do the opposite. You can bring the cursor back to where you started and then start moving it to the left. And then you'll start zooming in on smaller and smaller objects. So the next one we see is we're zooming in, we see a grain of rice here and an ant, and a coffee bean. If you keep moving it to the left, you'll see a skin cell here and a silk fiber. Keep moving it to the left, you can go down to the size of a cesium atom and a carbon atom here. And you can go all the way down to the left. You'll see things like strings, the strings they talk about in string theory, and Planck length, very, very small. And we'll see some more of those as we go through the lecture. So the second cognitive tool that we're going to look at is scale models. And I'm sure you're all familiar with scale models. You see the plastic models, like here you see one of a rocket ship, and you'll often see them in stores of model airplanes or cars. But right here in Raleigh, we have a giant scale model. And I don't know whether you can guess what it is. There it is. It's the Daily Planet, which is 70 feet in diameter. And it's a scale model of the planet Earth. And according to Chris Smith, who's, I believe, the coordinator of science programs at the museum, this is the second largest Earth on Earth. So it's quite a sight to see when you get down there. And if you walk across, there's a walkway over here. If you walk across, you can get a good view of North America and the United States. You can see the topographical features here. So it's worth taking a few minutes to take a look at this when you get to the museum. I did in prior astronomy days where we had them in person, I did an exhibit. It was called If Earth Were the Size of the Daily Planet. And it used the Daily Planet as a scale model. And if it said if the Earth were 70 feet in diameter, how big would the different parts of the planet be? So there were some surprising facts there. So each inch on the Daily Planet would represent 9.4 miles. So that at that scale, Mount Everest would be half an inch or 0.6 inches off the surface of the Earth. That's how high it would reach. Another surprising fact is that the average depth of the oceans on Earth is about 3 miles. But at the scale of the Daily Planet, it's only like a third of an inch, which surprises a lot of people. I think it would be much deeper than that. And then one other fact is that the tectonic plates on Earth at that scale would be, for underneath the continents themselves, it would be about 8 inches thick. And underneath the oceans, they would be about 3 inches thick. And the difference in the thickness between the continental and the oceanic plates helps you understand how subduction works, how when those plates crash together, the oceanic plate will move underneath the continental plate. So now, here's another scale model. It's also called Scales of the Universe, and it's at the Hayden Planetarium in New York. And this is the Hayden Planetarium. I don't know if how many of you have been there, but if you ever get to New York, you must see this. It's a wonderful place to see if you're interested in science. So it's a glass cube. The building is a glass cube, and this sphere here is 90 feet in diameter, and it's divided into two halves. The top half is a planetarium show. It's a theater, and the bottom half is another theater called a Big Bang Theater. And we'll talk about those soon. So here's another view of the museum. It's the New York skyline. And you can see inside there's some objects. Like here, it looks like Saturn. Yeah, and it is Saturn. Now I'm going to describe what you see when you go inside. So now here, when you go inside the building, you'll come in through this door over here, and you'll start walking around this square walkway, which is around the large sphere. And as you walk around, you'll see these stations along here, along the left where these people are standing. And each of those stations, you walk along there and you read what it says. And each of those stations use the large sphere as a frame of reference to compare with another object that's along the walkway. So for instance, when you get to the first one, what it says there, it says, if this large sphere represents the observable universe, then the object that you see in front of you, which would be the small sphere, represents the size of a supercluster of galaxies in relation to the large sphere. So then you walk down and you stop at the next station, and it says it ratchets down so that now the large sphere represents a supercluster of galaxies. And it says if the large sphere represents that supercluster, then the object that you see in front of you represents a cluster of galaxies. And you keep going, and the sphere keeps representing an object that's smaller and smaller. And so you get down to where the sphere represents the Milky Way galaxy and the solar system and the sun. And when it gets to represents the sun, these spheres here are the planets. So you can see here, this is probably like Neptune. And you saw in the other picture, there was Saturn, and all the other planets are arrayed around it. So it's very interesting. Then when it gets to the size of the Earth, it keeps going all the way around the other side until it gets to the size of a skin cell, and then it goes down to molecules and atoms and subatomic particles. So that's probably one of the premier scale models on Earth. And as long as we're at the Hayden Planetarium, they have something that is related to another cognitive tool called timelines.
Excuse me,
And
Rob?
yes?
We have a question about the previous screen. Could you go back one, if that is
Sure.
possible? Because we had Jennifer asking if the top one, if that was Jupiter.
Oh, yes. Yeah, you're right. It is Jupiter. Yeah, I'll answer the questions at the end because I have a large amount of
I
material
apologize.
to go over. I want to make
Thank
sure I
you.
cover it. Okay, so now we're going to look at the timeline at the Hayden Planetarium. And the lower part of that sphere is the Big Bang Theater. And you'll see a program in there describing what happened at the Big Bang. And then when you exit the theater, you start walking around the spiral walkway that comes down here. And that walkway represents a timeline from the time of the Big Bang all the way down to modern day. And each step at that scale will represent 75 million years. And there's 180 steps there, so that the age of the universe would be 13.8 billion years. And there's stations along here as well, and each of those describe what's going on in the universe at that point in time. So you could see where stars first formed, where galaxies formed, where our Milky Way formed, and when life formed on Earth. And so when you come down here to the end, at the very end, you'll see a small plexiglass cube, and embedded in the cube is a human hair. And it says, at the scale that you've just been walking, the width of that human hair represents all of human history. So recorded human history, 2,000 years. So, and down here, they have all kinds of wonderful displays, everything from black holes to plate tectonics on Earth. So there's a lot to see there. So now here's another timeline method that I'd like to show you. It's pretty popular. It was popularized by Carl Sagan. It's called a cosmic calendar. And what it says is that if the age of the universe equals a calendar year, then there are 38 million years per day. And I'm going to show you, this is showing you key dates in the cosmic calendar. And on the left, you'll see the date on the cosmic calendar. And on the right-hand column, you'll see the number of years ago that represents. So the Big Bang occurred on January 1st, and that was 13.8 billion years ago. Then the Milky Way galaxy formed 11 billion years ago. That was on March 15th of the cosmic calendar. Our sun formed 4.6 billion years ago. That would be, we're already more than halfway through the year. That would be August 31st. And then we're going to look at the evolution of life here. And first life formed on Earth shortly thereafter, 21st of September. Complex cells and first multicellular life formed on 1 billion years ago. And that was on the 5th of December. We're in December already on the calendar. And you can look at some of these other things going on here. Mammals didn't show up until 200 million years ago. That would be December 26th. And then on the next to the last day, 65 million years ago was when the dinosaurs died out. That would be at 6 o'clock in the morning on December 30th. So now from that point on, you have to go to a clock to represent the last day, see what's happening in the last day of the year on this cosmic calendar. So primates formed or were found 65 million years ago. That would be on December 30th as well. Hominids showed up at about 2 o'clock in the afternoon on December 31st. Primitive humans this is like 10:30 at night on the last day of the year is when primitive humans showed up. Anatomically modern human beings 200,000 years ago, that would be with 8 seconds left in the year. In agriculture, the first dynasty of Egypt was when there's only like 12 seconds left. Here, that was 5,000 years ago. We're talking in thousands here. Then the Roman Empire, the age of Christ, was 2,000 years ago. That would be with 5 seconds left in the year. And finally, modern science, technology, the American Revolution, and things like that all happened in the last 500 years. And that was in the last 1 second of the cosmic calendar. So that gives you a pretty good kind of frame of reference as to where all these events stood in the time. And then we come to the next analogical tool, which is analogies and proportions. And this is one of my favorite books. It's called A Bee in a Cathedral and 99 Other Scientific Analogies. And what the title refers to is it's making an analogy of a bee in a cathedral to the nucleus of an atom. And it says if the bee represents the nucleus of an atom, then the cathedral would represent the size of the shell of electrons around the nucleus. And in the introduction to the book, there's a very interesting quote, and it says, "Analogies have great power because they tap into the architecture of the human mind. The mind evolved in a complex and fluid environment and has specialized to process often partial and incomplete information in a quick and efficient manner. We find it easier to reason by comparing unfamiliar with familiar, falling back on experience, looking for links between things, and seeking out pattern and meaning." So I'm going to show you an example of a very good analogy. So electricity is an analogy. It's like water. So here on the left, you see an electric circuit, and you have a battery tied to the wire, connected to the wire, and it has voltage going across the battery and providing pressure as current to a light bulb, which then can light up, and it brings the electricity back to the battery, connects the circuit back to the battery. So if you think of a series of connected pipes, the analogous part of the pipe to the battery would be a pump. And so the pump is pumping water through the pipe, and the pressure of the water in the pipe represents the voltage. The current is the volume of water that's being pumped through. So there's a difference between the pressure and the volume of water going through. You could have a lot of pressure and not much water going through. So the current is the volume of water going through. That's what's coming through here and lighting up the light on the left. And on the right, it's the amount of water coming through. And then the resistance, which is the light bulb on the left, could be analogous to some sand, which is blocking the pipe in here. So now we're going to look at something, we're going to look at an example of an analogy and how it's properly expressed. So I'm sure some of you have seen these expressions in things like the SAT test. So now here it is. A hand is to, or a glove is to a hand as a sock is to what? So it would be, of course, to a foot. And you see questions like this on the SAT. They're a lot more, complex than this, but that's the proper expression of an analogy. And guess what? A proportion is expressed in the same way. So now you use numbers instead of concepts. So now 3 is to 6 as 5 is to what? To 10. Okay, now we're going to go back to the scales of the universe, the zoom in, zoom out tool that we used before. And we're going to go down to where it shows a carbon atom. So now you have carbon atom here. We're going to look down in the lower right. You can see it says 10 to the minus 9.7. So that's how large the carbon atom is. And then we're going to move the cursor to the right. We're going to go back out to the size of the Earth. And you can see that it's 10 to the 6.9. So what we're going to do is we're going to average those two together. So we're going to take the exponential scales, which is the minus 9.7 from the atom, and the plus 6.9 from the Earth, add them together and divide by 2, and we get an average of minus 1.4. We're going to move the cursor back to where it shows 10 to the minus 1.4. And what is that? So here it is, 10 to the minus 1.4. What shows there? In orange. So now we can construct an analogical proportion. And here it is. An atom is to an orange as an orange is to the planet Earth. That's amazing. Because, and it, in this one sentence, it described better the relationship of sizes than maybe a whole chapter in a science textbook. Because you know how big an orange is, you have a fair idea of how large the Earth is. Now you can use those ratios to imagine how small an atom is. So here we have a view from about 20,000 feet. And if you look at this little dot here, that's a house. And imagine in that house is a kitchen with a counter, and on the counter is in orange. What you see in this picture represents only about 5 miles across. So that tiny, tiny orange on that counter is in a picture only 5 miles wide. The Earth is about 8,000 miles in diameter. So the ratio of the size of that orange to planet Earth is the same as the ratio of the size of an atom to that orange. So now we're going to look at a more extreme analogical proportion. And this is the LIGO detector again. And as I said, these arms are like about 2.5 miles long, and they bounce a laser beam down each one. The laser beam comes in from the left along here, gets split, and the two halves of the beam get sent down to the end of the arms on each side, and they bounce back and forth off a mirror many times, then they get combined again. And if they're out of sync when they come out, they know that there's been some disruption in the dimension of space on one of these arms, and they can figure out how large that is. And what is the scale of these gravitational waves? They are incredibly tiny. They're about 1,000th of the diameter of a proton, which is, very, very hard to imagine. So we're going to, here's a view on one of the scopes that they have inside the LIGO, showing you what they see when they detect the gravitational wave. And you can see it just comes in as this. It starts out low and then it ends in a higher pitch. It just goes zip. Sounds just like that, zip. So one of these gravitational waves is to a human hair. Yes, this is a human hair, as a human hair is to the star Pollux. Pollux is about 10 times the diameter of the sun. And the sun is 100 times the diameter of Earth. So the ratio of the difference in size between the human hair and the star Pollux is the same as the ratio of the size difference between a gravitational wave and a human hair. Yeah. Holy cow. Yeah, hard to imagine. But these cognitive tools are very powerful, and they'll give you a much better understanding of these differences in size. So our last cognitive tool is thought experiments, and these have a long history in science. And Albert Einstein was fond of them. He used many of these, and one of the most famous is where he had twins, and one twin gets on a rocket ship and travels at near the speed of light for several months and comes back to Earth. And the other twin who remained on Earth meets his twin and finds out that he's much older than the twin who went into space. He's like 30 years older than the twin who went out into space and traveled near the speed of light. Another thought experiment that's famous, this is Erwin Schrödinger and his Schrödinger's cat thought experiment, most people know about. And it's an example of quantum superpositions, how an atom can exist in two different places at the same time. I can't get into too much detail. It's a little bit complex, but those are two very famous thought experiments. So now we're going to do our thought experiments. We're going to use sand to represent stars. So what if every star were a grain of sand? So how many stars are in the universe? Well, we had that question at the beginning of the session. So the Hayden Planetarium in New York estimates there are perhaps this many stars in the observable universe, 46 trillion. That's 4 times 10 to the 22nd power, or the equivalent of 100 billion stars in each of 400 billion galaxies. So now let's look at sand to represent that. So in 1 cubic inch of sand, fine sand, there's about 1 million grains of sand. So if you took 100 grains of sand and lined them up in the palm of your hand, you'll see that it's about 100 grains of sand long. So now here's a cubic inch here. You'll see here 100 inches on, or 100 grains on one side times 100 grains on the other times 100 grains deep. 100 times 100 times 100 is a million. So that means if you do the math, if there's a million in a cubic inch, that means that there's 1.7 billion in a cubic foot. So if we divide the number of grains of sand that represent all the stars, that's 46 trillion grains of sand, by 1.7 billion grains per cubic foot, you will get 23.1 trillion cubic feet of sand to represent all the stars. So how do you visualize that? So the land area of North Carolina is 48,700 square miles, or 1.35 trillion square feet. So dividing 23.1 trillion cubic feet of sand by 1.35 trillion square feet, you get 17 feet of sand. So this means that you could cover the state of North Carolina in 17 feet of sand if every grain was a star. Now let's look at that a little closer. So imagine North Carolina covered in sand. So that might look something like this. So here's a map of North Carolina. Here's Murphy at the western edge of North Carolina over here. And over here on the right side, it's Manteo on the coast. That's 545 miles. You could drive 9 hours at 60 miles per hour without stopping to get from one place to the other. Now imagine driving along there and looking up on the side of the road and seeing on each side 17 feet of sand as you're driving by. And each cubic inch of that sand contains 1 million grains. So now, to give you a better idea how deep 17 feet of sand is, a tractor trailer is about 14 feet. So it could cover a tractor trailer with 3 feet to spare. So now let's use those same grains of sand to visualize not only numbers of stars, to look at distances. So the distance from the Earth to the sun is 93 million miles. It's also known as an astronomical unit, 1 astronomical unit. So here, if this is the sun, then Earth is 1 astronomical unit away. And in that model, if the Earth were a grain of, or the sun were a grain of sand, that would be, the Earth would be 1 inch away. So now we're kind of constructing a little model here where the sun is a grain of sand and Earth would be 1 inch away. Earth would be much too small to see at that scale. But let's look at, move out a little bit farther. The nearest star to the sun is 4.2 light years away. Light travels 186,000 miles per second. That's also 5.9 trillion miles in 1 year. So if we do the math in our scale model where 1 inch equals 1 astronomical unit, it turns out that 1 mile almost exactly equals 1 light year. So now, if the nearest star is 4.2 miles away, if here's the sun as a grain of sand, Proxima Centauri, which is the nearest star, instead of being 4.2 light years away in our scale model, it's 4.2 miles. So if I was standing next to you and you had a grain of sand in your hand and that was the sun, and I had Proxima Centauri in my hand, to be at the proper scale of distance, I would have to move 4.2 miles away from you. Now, in between us would be hardly anything. I mean, there is, gas and ice in between us, very small particles, but it's really hardly anything. So now I want to do a concept here that we should bookmark for another slide coming up. If you took that 17 feet of sand covering North Carolina, if you rolled it up into a sphere, it would be 6.7 miles in diameter. So hold that in the back of your mind. So there's the 6.7 miles in diameter. At the same scale, how big would the observable universe be? So the observable universe is 93 billion light years in diameter, which includes the expansion of space itself. So in our scale model where 1 inch, or this should be 1 mile, equals 1 light year, the universe would be 93 billion miles wide. So now here, this is an illustration of the cosmic background radiation, which we're going to use to illustrate the size of the universe. So this is our scale model universe. If you shrink it down by a factor of 5.9 trillion, so that each star is a grain of sand, this is how big the universe would be. Then in comparison, this is the actual scale size, or this is the actual size of our solar system. So this is the actual size of our solar system compared to the scale model universe. So even after you shrink the observable universe by a factor of 5.9 trillion, it's still about 16 times wider in diameter than our solar system, our actual solar system. Now, remember our 6.7 mile wide sphere of stars? You would sprinkle that 6.7 mile wide sphere of stars throughout this 93 billion mile wide scale model universe. So the 6.7 miles versus 93 billion miles, there'd be hardly anything in there. So here, now let's change the scale of our model. And if you take that 6.7 mile sphere of stars that we were just talking about and shrink it down again, that sphere represented all 46 trillion stars. You shrink it again so that that 6.7 mile wide sphere becomes 1 grain of sand. So all 46 trillion stars are now that 1 grain of sand. We're not compressing the volume of the stars. We're just changing the scale from 5.9 trillion to 1 to 250 quintillion to 1. So now what happens? So if all the stars were the size of a grain of sand, the comparable size of the observable universe would be the size of the lower 48 states, the continental United States. So now imagine yourself standing in the middle of Kansas, in the middle of a field there, and you have this 1 grain of sand that represents all 46 trillion stars. That you would have to scatter those throughout the continental United States to match what's in the scale model, what's in the actual universe. Wow, yeah, it's hard to imagine. So now let's go do it in analogical portion. And we're going to go all the way from the left-hand side back. This is the scales of the universe again. We're going to go from all the way on the left, 10 to the minus 35th meters. That's Planck length in quantum foam and a string here. We're going to go all the way to the right, which is the size of the observable universe. So that's 10. We're going from 10 to the minus 35th to 10 to the 27th meters. So now we're going to average them. The minus 35 for the string and the plus 27 for the observable universe. Add them together and divide by 2 is minus 4. What do we see when we bring the cursor back to 10 to the minus 4th? We see a grain of sand. So now we're going to do the ultimate analogical proportion, which is, and this is using actual sizes, there's no scale models here. In string is to a grain of sand as a grain of sand is to the observable universe. You must be kidding. No, I'm not. It's really that amazing. So imagine this grain of sand in your hand, and comparing it to the observable universe, the real, actual observable universe is the same as the ratio of the sizes between a string or Planck length and a grain of sand. So that's the presentation. If you have any questions, I'd like to try to answer them.
Thank you so much for explaining it so well. I mean, it's really interesting to lay it out so that you can actually see how many tools you have, to kind of like see proportions, and because that's so important, especially when you're, working with scientific, parameters and things like that. We do have, I'm just looking at the chat right now, and it seems the first question that just came in is, so what is the size of the whole universe? I know you were talking about the observable one, but it's probably more, right? It's probably
Yeah.
extending.
If I go back a couple of slides.
And I'm just letting you know, Ron, there are already a lot of our participants that are using your H-Twin website,
Oh, yeah.
because they were, chatting in the chat about how interesting it is. So thank you for sharing that tool with us.
Yeah. Yeah, the observable universe is 10 to the 27th meters in diameter. So that's approximately, I believe, 93 billion light years in diameter. Now, people would think that if when the James Webb Telescope is going to be looking out to the edge of the observable universe, that's 13.8 billion miles. So they think, well, if it's looking from the center here to the edge, which is 13.8 billion, then the whole thing should be about 27 billion across here, 13.8 here and 13.8 here. That's 27 billion light years. But the universe has been expanding. The actual universe has been expanding since the Big Bang. So it's not just 26 billion light years in diameter. It's 93 billion light years in diameter. So the difference between the 26 and the 93 is how space itself has been expanding.
And that is very interesting. Yeah, we have time for, I believe, one more question. And Kai was asking, because we all know that there are suns in the universe and in our Milky Way, right? Would that, would this tool also help us to kind of like give an estimate of how many suns there are?
How many, what was that?
Suns, like how many
Suns
stars? Yeah.
in the Milky Way?
Well, in the
Yeah,
universe, in the observable, because you can probably extrapolate, right? Like if
yeah,
you
yeah. I'm assuming that, when I say stars in the universe, that would be the equivalent. Each of those stars would be somewhat equivalent to our sun, although the sizes of stars really vary
very.
enormously.
Mhm.
Uh, some of the stars are thousands of times the diameter of our sun, the red giants, and you have brown dwarfs that are very small, but they are all technically stars. And when I say there's 46 trillion stars, or when you see that estimate, it includes both of those, from the red giants down to the brown dwarfs.
Right. Yeah, yeah. Yeah, it's just fascinating. I mean, the galaxy itself is just fascinating. And also the fact that there's so much emptiness there as well, right?
Yes,
So that's
yes,
also
most,
something that you really don't think about, because when you look at that, you see all those stars and you see all the lights, but you don't realize how much
yeah,
space there is.
yeah. And when you see those pictures from Hubble, the Hubble Deep Field, the way that they estimate the number of stars is the deep field uh, from the Hubble. It focused on a small patch of the sky, and they focused there for a few days, just left it focused on that small patch, and they thought there was nothing there. But when they used a computer, analyzed the time lapse, they saw there were thousands and tens of thousands of galaxies in that small patch that they were looking at in the sky. So from that, they extrapolated to their estimate of the number of stars in the universe.
Yeah, that's quite a discovery. Well, thank
Yeah.
you so much, Ron. This was
Oh,
a
you're
very
quite welcome.
interesting talk. Thank you so much. And thank you everybody else for joining us today. We also want to thank our sponsors, the NC Space Grant and Pepsi, and of course our museum members. And if you are not a member yet, please consider to become a member with us. There are so many perks attached to it. You can also get like some, I think, 10% off on, the astronomy t-shirts and things like that. And so we do have a lot of other talks up until Sunday. And I believe our moderator, Cindy, will put the link to the schedule in the chat. So please check that out. The talks are free, but you do have to register. And also we have recorded this program. So if you want to see it again, it will be posted on our YouTube website. And with that, thank you so much, Ron. This was such an interesting talk. Thank you so much, everybody. I hope to see you on the next program. Have a good day. Bye.
Bye.